Hello, my name is John Cagnol. I'm a professor here at Central Supélec, University Paris-Saclay. I work at the MIX laboratory, which is a laboratory on mathematics and computer science for complex systems. I'm a member of the Federation of Mathematics of Central Supélec. I will be teaching you this class on partial differential equations throughout the semester. And today I will tell you what are the course objectives, what is the outline of this course, why is this course in the curriculum to begin with, what are the practical matters that you need to know, and a few references that can be of interest to go further in this class and also to understand better a few proofs that we will cover during the class. Let me start with the course objectives. The point of this class is to provide you with mathematical concepts that will be useful for modeling complex systems. And you will learn why partial differential equations are important in modeling and how to use them. You will also understand the main classes of partial differential equations. Well, to begin with, you will be taught what is a partial differential equation. You will also learn how to work with elliptic and parabolic PDEs, which are two classes of PDEs that we will describe earlier. Also, we will describe what is hyperbolic PDEs, even though we will not talk about hyperbolic PDEs and actually work with them in this course. You can do that in further classes, elective classes that will come along later in the curriculum, but for this class, we will only work with elliptic and parabolic PDEs. And again, I will describe that shortly in one of the next videos. You will learn about the distributions and numerical linear algebra. Now, this is really something that is absolutely fantastic. Distributions is a wonderful tool, and you will learn about distributions in this class. We'll also talk about numerical linear algebra, which is extremely useful when approximating solutions to partial differential equations. As you will see, very often we end up with a linear system to solve. That seems easy, but it's not that easy because the linear system is going to be huge. Now, from this course objectives, let me actually give you the outline of the class. Well, the outline will be modeling using PDEs, classification of PDEs. That's really the first thing that you want to know about PDE. Modeling with it and classify it. Then we will move toward elliptic PDEs. Elliptic PDEs is one of the classes that we will describe. And what we will do is prove the existence and uniqueness of solutions for PDEs that are elliptic. So that's something that the technique that you will learn in this class. And the technique is called the variational formulation. Now, in order to do this, you need tools that you do not know. You need concepts that you haven't heard before. And this is distributions. That will be a way to generalize functions. As a matter of fact, distributions are often called generalized functions. So we will actually embed our functions, not all of them, but many of them. We'll embed these functions in a larger set called the distributions, and you will see that this is a tool extremely useful to prove existence and uniqueness of elliptic PDEs. Very often, though, we cannot find an exact solution to the PDE. We cannot find the function by just saying, okay, here is the formula to give the function. So what we will have to do is to approximate the solution numerically, which means we will have to use a computer to find an approximate solution to our PDE. There are techniques for this, and you will see the finite element method. We'll explain how the finite element method works, and we will also see the finite difference method. And by the way, we will also introduce a library, Phoenix, that will allow you to do this easily. But before we actually do this, we need to understand how this works with our hands, really hands-on understanding how these things do work, and that's important, and we will do that in this class. As I said, one of the main problems will be to solve a large system, a large linear system. And as I said, it really seems like linear system is easy because you've seen like what, 3 by 3, 4 by 4, you probably did a few by hand at some point, but here we're talking about it can go like a million by a million. So hopefully, we have efficient algorithms to solve these systems, but we need to talk about the strategies to solve very large systems with a computer. So this is what numerical linear algebra will be about. And then we will talk about parabolic PDEs. And we'll see that parabolic PDEs can be, well, we'll use elliptic PDEs, and we'll also use what we call ODE, which is something that you probably already know, ordinary differential equation. So basically, you will see that parabolic PDE will just split the variables. One variable should be called the time variable, and we'll just deal with that with an ODE, and space variable, which we will deal with an elliptic PDE. So we'll come back to that when it's time to talk about parabolic PDEs. But what I'm saying here is obviously we're going to have to talk about ordinary differential equations, which are just a very specific case of partial differential equations. We just happen to have one variable. So actually what we're going to do is we're going to start with that because it's easier and it's also something that you might already know. So we'll just go back to ODE, and that will be our chapter 1. After which we will discuss modeling using PDEs and classification of PDEs. That will be chapter 2. Before we start with proving existence and uniqueness of solutions, we need the tools to do so. So that will be chapter 3, and that will be distributions. After which, we can start with the variational formulation for elliptic PDEs. That will be chapter 4. Then, we will introduce the finite element method. That will be chapter 5. And the finite difference method. That will be chapter 6. And as you can see in both chapters 5 and 6, as you will be able to see, we will need to solve these large systems. And so we'll come up with strategies for doing so in chapter 7, numerical linear algebra. And at that point, we'll be ready to introduce the next step, the other class of PDEs we'll actually deal with in this class, and that will be parabolic PDEs. So that is the outline of this course from chapter 1 to chapter 8, 8 chapters. Chapter 1 and chapter 5 will be slightly longer, so you will have more time allocated in your timetable because of it. All other chapters will basically be about the same length. All right. Okay. Now, why is this course in the curriculum? Well, I'm going to tell you because it is an important course. It is fundamental considering how the Central Supélec curriculum is positioned in the world. And we have, basically, I was the one in charge of putting together this curriculum when we merged Central and Supélec in 2015, and the first class started in 2018. It was a 3-year endeavor with a lot of people, and what we did was to put together this statement of objectives. That was one of the first things we did, and you can actually download it if you're interested in it, and I hope you will be, and you will understand why mathematics, PDEs, convergence, integration, probability is so important to the curriculum. Let me say that Central Supélec students should be able to use mathematics as a tool. Well, that's pretty much a given. Every engineer needs to master mathematics as a tool because they will need that. Everybody needs Fourier transform at some point in their life, right? And we just had a class on convergence, integration, and probability that's just about to finish, as you know. And it's important you know how to do Fourier. But it's also important that besides using Fourier, you understand what happens when the function is in L1 or in L2, and you need to understand measure theory, and you need to understand general topology, and you need to understand all of these things because you need to understand the foundations of mathematics. So we do believe that a Central Supélec student should be able to do two things in mathematics. Use it as a tool, And again, that's pretty much a given. Everybody would agree on that. But also understand the foundation of mathematics. And the latter is necessary if you want to model complex systems, if you want to unify existing concepts. For instance, in convergence, integration, and probability, by understanding measure theory, all of a sudden, the integrals, the series, and probability can just be dealt with kind of the same tools, you see? And again, I'm using convergence, integration, and probability because this is just a class you had, but the same will apply here in this class. I mean, this will allow you, understanding the foundations of mathematics will allow you to unify concepts that would be far away and apart if you did not have the high-level knowledge that allows you to unify these concepts. And that is important if you want to advance new concepts. We don't expect you to play a script. We expect you to write the script. So it's really important you understand the foundations because the tools you're using today are not necessarily the tools you will need tomorrow. So it's really important that both you use mathematics as a tool, but also understand the foundation of mathematics. And this is why this class on partial differential equation is a mandatory class for every single student at Central Supelec. Now, let me tell you a few things about practical matters, and let me be more precise about what I call practical matters. How do you learn on an online class? Well, first of all, I would like to say that we don't have a choice. I mean, as you know, there is a pandemic going on and we had to go online. So, you know, I mean, it's not like we have a choice. We can make the best of it. Online classes are good. I mean, you know, they're good for a lot of people. They're good for a lot of people because you can stop the video at any time. You can rewind. You can fast forward if you think I'm going too slowly. So there is a benefit during online classes. This is good. Of course, I prefer to teach face-to-face. I really miss you guys. I miss my Agomoro chalk. I mean, there is a lot of things I miss, but you know what? I mean, that's just the way it's going to have to be. So let's just make the best of it. Now, what happens here is I'm going to give you a few tips on how you can understand better and work well in this class. The way that you're gonna learn PDEs is every week you will have to go through 4 steps. The first step is watch the videos. I will post the videos online and you need to watch the videos. Now, when you watch the video, there is something extremely important. You need to take notes. And I'm going to repeat this again. You need to take notes. You need to basically write the course exactly as if you were face-to-face, right? You would not show up in class and just listen to me and not write anything, right? But that is the same thing here. You need to basically completely, fully take notes about this class. It is important for several reasons. The first one is, by doing this, you will learn better. The second thing is, there is no way 3 weeks down the road, you will be able to remember what theorem is what. I mean, you need to have this on paper. No handouts, no book is going to replace your note. So don't call me and ask for a handout. No, that is, I mean, your notes are extremely important. You need to take notes. That's the first step. Watch the videos and take notes. Step 2 is to prepare for the lab sessions that will be coming right after basically the lecture. I mean, if we were in a face-to-face, we'd have lectures and lab sessions, recitation if you prefer, and the same thing is going to happen here. The lab sessions will be online. So what you need to do is to make sure you have understood the material before the lab session and prepare the problems that have been assigned. I mean, every week I'll say, okay, well, you need to prepare this problem, that problem. You need to work on these problems before showing up to the lab session, or showing up to the lab session, even though even though you do that from home, you're still showing up virtually. And so it's important you have prepared the problems that have been assigned and that you have understood the material. Step 3 is actually the lab session. So that will take place at a given time, which is on your schedule. So make sure that you are connected ahead of time. And it starts with a quiz. So it's important to make sure that you have understood the material. Before the lab session, you will have a quiz that will be graded, and the grade will count toward the overall grade. So it's really important that you take the quiz and that you do it very, very carefully. Now, of course, because the quiz takes place before the lab session, we will make sure that the questions that are asked are questions that are pertaining to things that are easy enough. So if there is something that you missed, you can still ask the question during the lab session. That's the point of the lab session. So it won't be very difficult, but we want to make sure that you have watched the videos and made an effort to understand the material before the quiz, before the lab session. Otherwise, the lab session will not be as useful and productive as it could be if you did. And then you work with your lab instructor, ask questions, be active, make sure that your camera is on, and just work with your lab session instructor and the rest of the class toward the problems. That is step 3, participate in the lab session. And when this is done, basically you wrap up, you make sure that everything is crystal clear. If something is not crystal clear, then you absolutely need to understand exactly what's going on. Don't say, well, I think I understood, but I'm not sure. Okay, if you're not sure that you understood, then let me break this to you. You didn't. So make sure everything is crystal clear and go back to your notes, go back to the notes you took during the lab session, go back, but make sure that everything is crystal clear. All right? That is basically the way to succeed in this class. I mean, and that's going to be every week. We have 10 weeks together, 8 chapters, but as I said, we are in a situation where, 2 chapters will actually have a longer period of time. So that is what's going to happen. Watch the videos, prepare for the lab session, participate in the lab session, and wrap up. Now, there is a lot of information on the syllabus. I suggest you go online to EduNow. Check the syllabus. It also contains the grading policy, how you will be evaluated, how many percents of each grade is coming into the overall grade. So make sure you understand, you read this document carefully. It contains a lot of information, which is very useful. I like to finish this introduction by giving you a few books, a few references that I used myself to make this, to create this class, and that will allow you to go further, and also sometimes we will refer to these books for proofs. Now, the first reference is the lecture note by Eric Herbin and Pauline Lafitte, who really have put together this CIP and PDE class. I mean, when in 2015 to 2018, we put the new curriculum, Central Supélec, together. Basically, I put them in charge of creating the CIP and PDE class, and they did an outstanding job. And now I'm teaching this class, and I think that it's absolutely fantastic. And they actually wrote a lecture note, which you were given this lecture note. So that's the first reference I would actually provide. Another great reference is Haim Brezi's Functional Analysis of Spaces and Partial Differential Equations, which is now available in English. That book was basically my bedtime story when I was a graduate student. It's a wonderful book. Really, I mean, if you understand this book, it's fantastic. So really, I strongly recommend the Brezi's book. And again, now it's available in English. Here are the references of the book in English. There is also the Grégoire Allaire book, Numerical Analysis and Optimization, an Introduction to Mathematical Modeling and Numerical Simulation. And I strongly suggest this book by Grégoire Allaire. And that is the third reference I would like to give for this class. And the fourth reference I would like to give is actually a little bit on the side. It's Solving PDEs in Python, and that's a Phoenix tutorial. At some point, you will be asked to put together a few equations together in a project and solve this numerically. So we'll see how to do finite element method. We'll see how to do finite difference method. But when the problem gets a little complicated, then you're not going to do everything by hand. I mean, you need to understand how things work, and you need to know how to do this by hand for simple problems. But if it's really getting too complicated, and obviously you want to use libraries to help you doing so. And one reference for doing so is actually this book that I'm currently putting here as a reference. So that's it for this introduction. Welcome to the University Paris-Saclay. Welcome to Untitled Chapter. Enjoy this class and have a great semester.